Okay, so we're going to move on with our full forecasting toolkit now, and we're going to add a measure of uncertainty to our forecasts using what is known as a prediction interval. So we need to do this because we can never estimate exactly what a value is going to be in the future. But what we can do is use some statistical methodology to make inferences about what the most likely value of that will be, which is our point forecast, and what the uncertainty in that estimate is. So that uncertainty is called a prediction interval in the forecasting world. So in this lecture, we're going to learn the difference between a prediction interval and the classic confidence interval. So you may be familiar with confidence intervals from undergrad statistics classes. It is slightly different from a prediction interval, and what we'll see is that prediction intervals are generally wider than confidence intervals. We're going to do some practical things, so we're going to look at how we use those baseline forecast classes in Python to generate prediction intervals. So we're not going to focus on the underlying mathematics. We're going to focus on what does it look like, and how do you get that data out of a model. And we're also then going to very briefly evaluate the accuracy of a prediction interval, and we do that with something called coverage. So we look at how many of the true points in our test set are actually covered by our prediction interval. So we've got some standard imports as normal. Then there's a couple of helper functions to help with plotting the data, and there's some comments describing what they do. I won't go through those here. The data we're going to work with first of all is the ED data, but we're also going to work with the alcohol data at the end as a full example of how you produce a prediction interval and check its coverage. So we're just reading the ED data in here. We're doing a train test split on the, so we're holding back the final 12 months as a test set, and we've done a calendar adjustment of the data. So let's briefly talk about confidence intervals versus prediction intervals. So confidence intervals are all over the internet. You can look those up if you're not familiar with them. They're used heavily in statistics, and they're usually used to measure the uncertainty in a population parameter. But in forecasting, what we should be doing is using something called a prediction interval, because the two measure things that are slightly different. So these couple of paragraphs we've got here are just a kind of a thought experiment, and to explain the difference between a confidence interval and a prediction interval. So imagine that you are interested in estimating the mean height of adults in the UK. I don't know why you would want to do that, but for this scenario, assume that you're very interested in that. So you're standing in a room, you've got your own room for doing measurements, and you're inviting adults from the UK into your room one by one. You measure their height, and you jot that down in your notebook, and then off they trot, they go on, and then the next person come in. So you're going to repeat that for 30 people. And then when the last person's left, you very quickly calculate the mean height of those that random sample of people. So we call that the sample mean, and it's an estimate, our best estimate, of the true population parameter. So the true mean height of adults in the UK. But your sample is only 30, so it's a finite sample. So you need to recognise that the true mean height may be quite different from what you have measured there. So your estimate is subject to some sampling uncertainty. So how do you quantify that uncertainty? So what you use is called a confidence interval. So you may have heard of things like a 95% confidence interval. And what that means is, if you repeated that experiment 100 times, then you would expect 95 of those intervals that you calculate to actually contain the true population mean height, but 5 of them would not. So a confidence interval provides a statistical estimate of the distribution of that population mean, of that true mean, if you repeated the experiment many times. Now, the good news is you don't need to repeat the experiment many times. There's something called the central limit theorem, which you can invoke to generate those confidence intervals for you. So you only need to do that sampling once, and then you can fit a confidence interval to that. Very straightforward. So it's about observing values and then calculating the uncertainty in something like a mean. So it gives you it helps you look at the distribution of the mean. When we move into a forecasting context, we're interested in something similar called a prediction interval, but our task is slightly different. So now we're interested in the height of the next person that enters the room, so person 31. So that's a bit more difficult than estimating a population mean, because if you remember, what we did there was we observed 30 values and then we quantified the uncertainty, whereas this is an unobserved value. We don't know exactly what that's going to be. So a prediction interval must take into account both the uncertainty in the mean and also the random variation you see in each person that enters the room. So typically what that means is a 95% prediction interval will be much wider than a 95% confidence interval. And also, as we go further and further into the future with our forecast, those intervals will become wider, because typically it's easier to make forecasts closer to where you are standing in time than further away. So your uncertainty grows with your forecasting horizon. And we'll see that in the examples. So the key thing to remember is that if you hear someone talking about confidence intervals, that's not really what we're using in a forecasting context. We're using prediction intervals. And prediction intervals are about forecasting and getting uncertainty around an unobserved value from the future, whereas confidence intervals are using previously observed values. So let's have a look how uncertainty grows over time. So here what we're going to do is we're going to fit the ED training data to a naive model, a naive baseline. I'm going to now call the predict method again. I'm going to pass in horizon again of 12 months, but I'm going to follow that up with some additional parameters. So I'm going to say return predict int equals true, which means please return a prediction interval. And I'm going to say I want, this is basically the 80% prediction interval and the 90% prediction interval. So we're specifying this in terms of an alpha, which is 1 minus the interval that you want to get. So that returns a tuple, it returns the predictions, and then it returns an array of array, which is our intervals. So let's run that. And we're going to plot the prediction here. So I'm going to pass in the training data, the predictions, and the intervals. So now what we can see, in addition to the blue line, which was our point forecast that we've seen in a previous lecture, we also now have this yellow shaded area, and beyond that, a purple shaded area. So the yellow shaded area is an 80% prediction interval. So what this prediction interval is trying to do is give us a measure of uncertainty where we're saying, I would expect that 80% of the points in the future will lie between these boundaries. And then further on from that is the 90% prediction interval. And that's saying with a 90% probability, I believe that the future values will lie between these. So the higher that probability, the wider your prediction interval. Now these prediction intervals turn out to be very wide indeed, and that's because naive one isn't fitting the data particularly well. So there's quite a bit of uncertainty in the prediction. Let's just have a look if we call plot prediction again and this time pass in the test set, we can see what the true values actually were. And so the point forecast is quite good. So naive is a good method, it turns out, in this particular case for the point forecast. But in general, it's a poor fit to the data. So we get very wide intervals, far too wide. So we're saying in the yellow region that we would expect 80% of the time for those points to fall within there. And actually, what we're seeing is all of the points fall in there. So those intervals are too wide. And that's another important point. Although we want to capture that uncertainty, we want those intervals as narrow as possible to be useful for decision making. So let's have a look at evaluating a prediction interval in practice with another tricky example. So one of the things to point out first is that getting prediction intervals to be very accurate is very difficult in practice. So like with the naive model there, if the model is a very poor fit to the data, it might be very uncertain. So prediction intervals may be too wide in practice. While more complex methods may be overfitting to the training data. So they tend to be overconfident and their intervals might be too narrow. So it's trying to find a way, trying to balance between those two extremes. However, you should always be using prediction intervals in practice. But the question is then understanding how good are they at coverage and what are their limitations. So let's have a go at producing some for the alcohol data and then evaluating how good they are through their coverage. So I'm going to read the alcohol data in. I'm going to hold back 12 months. I'm going to do a calendar adjustment because it's daily data. And I'm also going to log transform the data because of the multiplicative seasonality. So I'm going to fit two models to that data. I'm going to fit this seasonal naive model with a period of 12 and naive one. And I'm going to return their predictions. So remember, they are log transformed predictions. So we'll need to back transform those for them to be useful. Okay, so let's back transform them there. Let's have a look at the mean absolute error of seasonal naive, which is 22, and the mean absolute error of naive 1, which is 56. So in this case, it looks like seasonal naive has a lower out of sample error than naive 1. So if you look, I've passed in the test set here and the predictions of that test set. So that's the out of sample error. And that's how we want to compare our forecasting methods. So my preliminary conclusion here is that seasonal naive is a better baseline method than naive one. And that's what I'll use in all of my comparisons with more complex methods. So now let's generate our prediction intervals and have a look at them. So again, I'm going to call seasonal naive predict. This time I'm going to pass in some additional parameters of return prediction interval to true, which means please return them. I'm going to pass in my alphas. I'm going to pass in 0.2 and 0.5, and that means I'm asking for an 80% prediction interval and a 95% prediction interval. You could ask for more if you wanted to, or you could just ask for one. And then I'm going to back transform both the point forecasts and the prediction intervals, and that's just by calling NumPy exponentiate. Okay, and then I'm going to plot those prediction intervals, and I'm also going to plot the test data, the true values. This slicing here, it just means that I'm going to plot the last 12 months of the training data, and that's just so that the prediction doesn't look really small in the plot. So here we go. So this is our training data up to November 2019 or December 2019, and then here is our January 2019 onwards prediction. So in blue, is the point forecast. In yellow is our 80% prediction interval. In purple or pink is our 90% prediction interval. And then in black is our true value. So what we can see is that the point forecasts don't always line up with the true values as we would expect. And also we see that the prediction intervals do capture a proportion of those points true values within their bounds, but not all of them, and we wouldn't expect them to catch all of them because they're not 100% prediction intervals. That's the concept that doesn't make sense. They're 80% and actually they're 95%, but I've labelled them 90 there, apologies. So what we can do is we can calculate the true coverage, and that's just looking at how many of these points fall within the boundaries. So there's a little function to do that for you in the forecast.metrics module. So bring that in, and we can just have a quick look at that. Okay, so coverage calculates the proportion of the true values that are covered by the lower and upper bounds of the prediction intervals. So we're passing in the true values, and then we're passing in a NumPy array of the prediction intervals, and that NumPy array is a matrix of length h, the forecast horizon, and width 2. So let's look at the 80% prediction intervals first. So only 50% of the data actually falls within those 80% prediction intervals. So that's a classic problem of the prediction intervals not being wide enough. And then the 95% prediction intervals, quite a lot better, but they're still not quite wide enough. But they are quite good. Now, bear in mind, this is obviously only one holdout sample. So in practice, like with the point forecast estimates, there may be some variation in these numbers. But this is a good basic test that you can do and should always do when you're building your forecast models. And the final thing to remember is that these are baseline methods. So ideally, what you would like is a more complex method that would come along and do better than these baseline methods in both their point forecast accuracy and their prediction interval coverage.